PIN means, as you see, okay. First of all, I should say this photodetector is just the same configuration as the LED or a laser diode, so-called P material and N material, sandwich of this P and N materials. So the P, N, and I means insulator. That means we created the insulator between the P area and N area for effective optical power to electric power conversion. Anyway, you will understand P, I, and the P-type material, N-type material. Between them, we will have an insulator layer. That means the middle layer consists of nearly intrinsic material between the P and N doped regions. Okay? And most of the incoming photons are absorbed in the intrinsic region, I layer. And the carriers generated therein can efficiently contribute to the hot current. That's electrical signal. So this means that because of such an insulator, good responsibility. Responsibility means output current versus input optical power change. And another one is avalanche photodiode, APD. We will use almost all the cases, or mainly a PIN, but sometimes APD. So the question, do you know APD, avalanche? Excuse me? Avalanche, English word. Avalanche, you know? Okay, okay. Avalanche. Okay. Sorry. Okay, I see. Why I asked you avalanche is that in Africa you don't see avalanche, right? Do you see avalanche in Africa? No. Because you don't have so much snow in Africa. Yeah? I know only the highest mountain, Kilimanjaro, in Africa. Kilimanjaro, only? Kenya. Tanzania. Sorry. Any other higher mountain, much snow? That mountain has snow? Snow? Oh, really? I'm sorry. It's my misunderstanding. So what I mean is that avalanche is often seen in the mountain in winter. You see? This, much snow go down suddenly. This is avalanche. So avalanche photodiode means that additional layer is added, in which secondary electron hole pairs are generated through impact ionization. This is a very long, sorry. It's very difficult to go back. Anyway. This figure, you mean it? Avalanche diode, in case of avalanche diode, this slope of PN region junction point, so very steep. So we say avalanche. Avalanche means that this electron or hole goes through so accelerated style, so like avalanche. So avalanche diode. Okay. Usually a PIN diode don't have so steep slope than avalanche diode, but avalanche diode has so steep, so very effective optical to electric conversion. The characteristics of avalanche photodiode is high responsibility, high responsivity, not responsibility, just responsivity of 2 orders of magnitude higher than the pin photodiode because of this steep slope of electrical field like avalanche. That's right. So then I will explain about the optical amplifier systems. Excuse me, normally do you take a rest or at 60 minutes or 90 minutes? What your preparation? Prefer? 60 minutes or 90 minutes? No problem? 60? Eh? At 15? 50? 15? Oh, okay, I see. 15. So anyway, can I continue? Or would you like to take a rest? Which? Sorry?
Normally, afternoon you take a break of 30 minutes.
Hmm.
In the morning, 30 minutes. The afternoon you take a break of 30 minutes.
Okay, okay.
We can decide what time you take that 30 minutes.
Sorry? Okay, okay, I see. Okay. So I will continue to 4 o'clock, okay? And take a rest, okay? No objections? Okay, I see. So if I sorry. If I can't finish this chapter 5 until 5 o'clock, I leave some materials on Monday morning. Okay? No problem? Okay. I will continue this, if necessary, on Monday morning. So optical amplifier systems means, sorry, something? So let's start. So this is optical amplifier system, the outline of optical amplifier system. As you know, this optical amplifier system transmits the optical signal through concatenation of optical fibers and amplifiers. So the signal from transmitter can be attenuated by the transmission fiber, but optical amplifier amplifies the signal level to the original level. But also they add ASE noise, amplified spontaneous emission noise. And after repeating this process, the signal can be reached at this receiver. Okay, this is very basic principle of optical amplifier system. And limitation in transmission distances means just generally fiber loss and waveform distortion. And loss limitation has traditionally been in the past overcome using regenerators, not optical amplifiers, just repeated the OE conversion there. And the regenerators has a complex and expensive and inefficient in wavelength division multiplex systems. That means we have to use a regenerator of OE conversion as a number of the wavelengths. But in the case of optical amplifier system, we may place only one amplifier to amplify WDM signal, many signals, 40 or 80 wavelength signals. And optical amplifiers' general characteristics are described in G.661 or 662. And that means direct amplification of the optical signal and the compensation for the fiber loss, no conversion to the electrical domain, or generation of optical noise. That means I said amplified spontaneous emission noise. And this device was developed the late 1980s. And the long-haul optically amplified systems are now widespread during the 1990s. So, so OA means optical amplifiers as a booster amp and a preamp. If you use characteristics, because this is a receiver noise, this receiver has a receiver noise, but we will add some noise, optical noise, by this preamplifier. So that means a low level of AS noise by use of narrow band optical filters. So we will often use narrow band optical filters to reduce the amount of ASE noise here. And next one is just optical amplifiers used as a line amplifier. This is the most commonly used case of optical amplifier. You use optical amplifiers for like as a repeater, or just say optical amplification of optical signals. So this type of applications definitely increase the regeneration length between passive fiber sections. That means the regeneration section means this and this. This has these TX, RX is OE converters. So this is called the regeneration section. And the compensation for branching losses in the optical access network, and that's also the same use of such line amplifier. And sometimes replacement of some old conventional regenerators in long-haul fiber section. This means that such a case that you once have such a system with electrical regenerator here, but after installation, you can replace this electrical regenerator by this optical amplifier. Conventional regenerators for compensating for signal distortion means this is not so significant. And sorry. This is just, say, EDFA amplifier configuration. EDFA means erbium doped fiber amplifier. EDFA is just erbium doped fiber excited by pump laser, also described in G.661 or 662. So this fiber is erbium doped fiber, and you will see this coupler. Coupler couples the pump power with the signal power. And signal power from here, signal in, and through this erbium doped fiber, and go out through this port. So then we will add this high power laser output from pump laser to erbium doped fiber. This erbium doped fiber acts as amplifier and amplify the optical signal. And of course, this type of amplifier easy to oscillate. So we don't need to oscillation of laser, like a laser. So we will use this isolator. Isolator prevents the reflection of the light. So isolator is necessary. So characteristics is a higher efficiency and relatively lower pump power, just is cost-effective lower power pump. And a good connectivity with transmission fiber. This is because, of course, this is a kind of fiber that you can easily connect with transmission fiber. So good reliability. This is also made by this characteristics, just fiber. And so reliability is good. Oh, sorry. And this is a principle of amplifier, optical amplification. You may know that in general, optical amplification or optical amplifier is the same as a laser. This is because as you see the laser, the term laser means light amplification by stimulated emission of radiation. So just you can understand that amplifier and laser, what the difference is. The laser has a mirror to oscillate optical signal. And amplifier don't have such a mirror to reflect the optical signal. And this is energy level model of optical amplification. In the case of laser, semiconductor laser, we apply the voltage between the p-n junctions to supply energy to the device. And the device converts the optical power, electrical power to optical power. But in this case, L-beam doped optical amplifier is pumped by light itself. That means pumping light, high power laser, will pump this L-beam ion state to a higher excited state. That's mean. And if higher pump laser is applied to the EDFA system, this is the energy level of L-beam ion, which is better, ion. And this excited state of L-beam ion will generate light. This is radiative emission. This is just nearly around 1,550 nanometers. And you will see such a broad spectrum noise as output of EDFA. So we say this is EDFA gain spectrum. This is maybe 30 nanometers or 40 nanometers, around 1,550 nanometers region. And we use pump wavelengths, mainly 980 or 1,480 nanometers. This is just, of course, 980 nanometers laser has a higher energy. That means in a quantum optics, you know, the energy of the light is h by nu. Nu is the optical frequency. Just means higher optical frequency is shorter wavelengths. So you can see 980 nanometer laser has a higher energy than this 1,480 nanometers laser. So in such a case, this is so non-radiative emission translates the transit this higher energy state to a lower energy state. And finally, the same radiative emission at 5,550 nanometers band. And what's the difference between these pump wavelengths? Actually, 1,480 nanometers laser pumping a higher efficiency because this process don't have such a non-radiative emission, so higher efficiency. But 980 nanometers pumping has a lower noise characteristics. This is because this pump can effectively excite the L-beam ion to the higher levels. Anyway, you only have to know that two kinds of pumping laser in EDFs. And the next one is semiconductor optical amplifier. Semiconductor optical amplifier is just the same configuration as semiconductor laser I showed in the previous slide. Almost the same configuration and no difference, except for the mirror. Of course, this amplifier has no mirror, of course. No, this is because this is just amplifier, not oscillator. So this type of device don't have a mirror. And it's not so important to learn about semiconductor optical amplifier because normally we don't use such kind of device, semiconductor optical amplifier in the system, only special case. And this is just same as semiconductor laser. And characteristics as amplification band is the same as a semiconductor material. Problem is in packaging or pigtailing or anti-reflection coating or high polarization sensitivity. That means that it depends on the polarization state. and some limitations in output power. This is because the semiconductor laser is very small, maybe 1 millimeter or less small one. But EDFA has a long, a few meters, so large cavity. So semiconductor laser has less output power. So relatively high noise figure, nonlinear response in the saturation regime, and the gain and first gating function. This is just a nonlinear response of semiconductor optical amplifier. And normally we don't use such characteristics in optical communications. So other applications, there's integration with the emitter laser diode to boost the power, or integration with optical switch or compensation for the loss, or signal processing devices, such kinds of devices for signal processing. So we don't see semiconductor optical amplifiers in actual transmission systems yet. Now. So the last one, optical amplifier, is Raman amplifier. So do you know Raman amplifier or Raman amplification? No? Okay. This is again Raman. Raman. Do you know Raman in optics? No? Raman. Hi. This is also name of Indian. Maybe nearly 100 years ago, Raman received the Nobel Prize due to this Raman amplification, discovery of Raman effect. Okay. And now we use this Raman amplifier in optical transmission systems. This is almost the same configuration as EDFA. So you have a pump laser from here, a signal from here, coupled and introduced to fiber. The difference is, what is the difference? Just EDFA has a L-beam doped fiber, and this Raman amplifier don't have such EDFA L-beam doped fiber, and just transmission fiber. Okay, but this fiber itself is maybe a few or tens of kilometers long, so long fiber, and pump signal are injected. Difficulty in placing isolated this. And the Raman effect is, I will describe later, nearly 4 o'clock, but and this is just fiber acts, transmission fiber itself acts as an amplifier. And the lower efficiency, that means the higher pump power is required, and good connectivity with transmission fibers, because this is just transmission fiber. The lower noise, exposure to high optical power. This is a problematic situation. That's optical safety issue described in G.664 because of a high power laser. So this is the principle of Raman amplifier. Okay. Again, I described this energy state level as EDFA, but in this case, pumping laser raises the optical fibers energy state itself to some excited state, and optical fiber will generate, or exactly saying, scatter the light, injected light, some shifted light in wavelengths. Because of this optical phenomenon means some molecular vibration of glass. The fiber is made of glass, so some molecular vibration of glass creates such a scattering, and you will see some light scattered, such scattered light just shifted from the pump laser wavelengths about 100 meters or so. So as the case of EDFA, you will see such a so-called gain spectrum. This is Raman gain spectrum. That means you can use Raman amplifier around wavelength region around here. So the important point is just Raman amplifier has just 100 nanometer shift from the pump laser. So you can place anywhere in the wavelength region the pump laser. So you can create anywhere you want. You can create this gain band anywhere you want if you choose the wavelengths of the pump laser. In the case of EDFA, you can't do such a thing that the optical gain band with optical gain band wavelength is generally fixed by the LB-ion characteristics. Yeah, and you also, that means the increase of bandwidth by multiple pump lasers. So you can use 3, 4, 5 pump lasers with different wavelengths, and you can have such a broad optical spectrum for gain bandwidth. So in most cases, we use such Raman amplifier, as a reverse pumped Raman amplifier. That Raman amplifier is placed near the end of transmission fiber. So we will use Raman pump laser here and inject high power laser to transmission fiber. So normally, the power of optical signal will decrease straight in this straight line to the output of fiber loss attenuation. But when you inject Raman laser here, the signal will amplify and increase the signal power in such a way. So pump is strongest at the receiver and the weakest at the transmitter. This means signal is amplified this weakest region. Another use of Raman amplifier is the forward pumped Raman amplifier, but actually this is not so important because at the output side of the system, transmitter output, the optical power is sufficiently high, normally sufficiently high. So you don't need to amplify more by Raman amplification. So this is less important case than the previous reverse direction pump. But anyway, I will describe some. So forward pumped signal output reference point is here. You will inject strong light here. In the transmission fiber, the signal will amplify. And this is the case most often used bidirectionally pumped Raman amplifier. It's just a combination of reverse pumping and forward pumping. And this is just maybe a transmission fiber in the length, 80 kilometers or 100 kilometers. So you can amplify the optical signal in the transmission fiber by Raman amplification. Okay, and this is the strongest. The pump power is strongest at both ends. Each pump at different waves for wide bandwidth amplification. That means you can use different wavelengths for forward pumping and backward pumping. So as I described, you can have different wavelengths pump laser in the same fiber. So you can broaden the gain bandwidth with this configuration. So this is just a discrete Raman amplifier. Discrete means just Raman amplification is confined in some box or devices, not transmission fiber. So this is just same as the EDFA, just a device of Raman amplification. Sorry. So this type of discrete Raman amplifier is used as the same use of the same as EDFA. So just amplify the optical signal in only this box. So you don't see the high power laser or something outside this box, no in the transmission fiber. So specific optical fiber, this is normally other than the transmission fiber, the specific fiber to reduce the needed pump power for achieving a specific gain. That means a very small core diameter. As you know, the nonlinear effect, it could be strongest in the smallest core region because optical power is concentrated in a small region. And some dopant will be necessary for increasing efficiency. So I will stop here at the end of optical amplification, I don't step in the next issue of optical switching. And we already passed the 4 o'clock, but I will accept any questions or comments here at the last of this week. Any comments or questions? No? Okay. I will have a presentation on Monday and Tuesday, so you will have a chance to ask me anything about the optical devices or something like this on Monday and Tuesday. So don't hesitate to ask me anything, okay? Thank you very much today.